Good afternoon. My name is Ethan Joseph, and I'm a sophomore at the Engineering and Science University Magnet School. And my project is named Implementation and Validation of a Novel Machine Learning-Based Mobile Mechanocardiography System for Arrhythmia Detection. So, I'd like to start off with a bit of a background on arrhythmia and cardiovascular diseases. So, cardiovascular diseases, also known as CVDs, are currently the leading cause of mortality worldwide. And arrhythmia, also known as irregular heartbeat, is typically indicative of these cardiovascular diseases. So, it's incredibly important in clinical settings that arrhythmia is detected to potentially mitigate these cardiovascular diseases. Now, currently, electrocardiograms, also known as ECGs, are used to monitor and observe heart rate. So, because the heart is a muscle, ECGs monitor changes in electrical potential across the chest and across the heart using a complex array of electrodes. Now, although this is quite effective and is predominantly used in clinical settings, it requires a pretty complex and involved setup process. Sort of on the physical side of things, the skin must be prepared for this array of electrodes, and then on the software and hardware side of things, uh, the these electrical signals are really small in magnitude, so a lot of signal processing has to be performed to reduce interference. So this figure in the bottom right, these two graphs actually showcase a normal ECG in comparison with an arrhythmic ECG. And as you can see, the arrhythmic ECG sort of lacks that pattern and that rigid pattern that's seen in the normal ECG rhythm. And the complexities around ECG have actually given rise to a field known as mechanocardiography. So uh, this field records physical motion of the heart beating in the chest as opposed to changes in electrical potential across the chest. And two primary techniques in this field include seismocardiography, SCG, which monitors changes in acceleration due to the heart physically beating in the chest, and gyrocardiography, GCG, which measures changes in angular momentum due to physical contortions of the heart as it beats. And it's important to note that the sensors required for mechanocardiography are incredibly accessible and inexpensive. The sensors in questions, accelerometers and gyroscopes, are incredibly prevalent and are also seen in all modern smartphones. And because of this, the viability of using smartphones for mechanocardiography has been researched and well established in literature. So, a smartphone based arrhythmia detection system using SCG and GCG has been implemented in the past. And this specifically used classical machine learning techniques for classification of recordings taken from a smartphone resting upon the chest. And because of the usage of classical machine learning algorithms, this ultimately required quite a lot of signal processing to actually generate classifications, and thus didn't really prove any advantages over ECGs and hasn't been used in clinical settings. And that leads to my project. The focus of this project was to develop a smartphone based arrhythmia classification system that uses a specific machine learning technique known as convolutional neural networks to generate classifications. So ultimately, the purpose of this project was to provide an interface for measurements to be taken from a smartphone resting on a patient's sternum, classified as healthy or arrhythmic, and also not require significant data preprocessing and manual processing as in prior work. So this flowchart towards the bottom of the screen here showcases the process of this project. Data sets containing these mechanocardiographic recordings were obtained. A machine learning model to classify them was developed and trained to classify these samples as healthy or arrhythmic. And finally, this was incorporated into a mobile app for effective testing in clinical settings. So this project used two data sets, the first of which was arrhythmic recordings, and the second of which was healthy recordings, and both of these included SGC and GCG data. So these recordings were originally obtained in a relatively unordered state. So one of the main steps of this process was processing and normalizing these into 30-second long samples at 200 hertz, meaning 200 individual measurements per second. And this ultimately yielded 560 trainable recordings split across the healthy and arrhythmic classifiers. So 280 healthy recordings and 280 arrhythmic recordings. And that's also visible in this table here, in which you can see actual data obtained from these data sets. Now, moving on to the machine learning algorithm used in this project, and this is largely the main focus of this project. I decided to employ a convolutional neural network. This is a type of machine learning algorithm that is very effective at classifying temporal patterns in large amounts of data. In this case, time series mechanocardiographic data. And because of CNN's ability to classify these patterns, they've been commonly employed in image classification solutions, and they don't require the extensive data processing that was seen in classical machine learning techniques used in previous work. So I personally developed my model based on the VGG16 architecture. This is a convolutional neural network architecture well established in literature. And ultimately, the final model had a 6,000 unit input, meaning 30-second samples at 200 hertz, yielding 6,000 total values, and output a 2-unit binary classification, meaning a probability of an individual sample being healthy or arrhythmic. Now, this model's training process was relatively straightforward. So the process data set was fed through the model with their respective classifiers. And the original data set was split with a 10% validation split, meaning that 10% of those processed 560 pieces of data was actually put aside and used only to evaluate the model and not to train it. So this model ultimately trained for 8 epochs, meaning that the training data set was fed through 8 times before it achieved maximum accuracy. So moving on to the results, this model obtained a 95% training accuracy. This refers to the classification accuracy of the model during training. So on data that it had previously seen before, on data that it's, quote unquote, learning. And finally, a 93% validation accuracy. So this is its classification accuracy on that 10% of set aside data that it had never seen before, had never trained on. And this sort of gives a look into its potential performance in a real diverse clinical environment. Moving on to this middle figure in the center of the screen, that is the model loss, and that signifies the discrepancy between the model's actual output and its confidence in that in relation to the expected output. So lower values are are sought after, and as you can see, the model's loss steadily decreased throughout the training process, showing that it was not only learning but also getting closer and closer to making perfect classifications. And this figure in the bottom right is known as a confidence matrix. And this signifies the model's accuracy in relation to predicting specific classes. So as you can see, the model had a 97.14% classification accuracy for healthy classes, whereas it only had a 94.29% accuracy for arrhythmic classes. And I personally hypothesize that this is due to an increase in variation through the arrhythmic classes, whereas these healthy data recordings were relatively linear and were relatively constant. So a mobile application was developed to facilitate an intuitive and easy to use clinical testing process. So this was developed using the Flutter cross-platform framework, meaning that it's able to run on both Android and iOS platforms, and it's able to programmatically obtain device gyroscope and accelerometer information over a 30-second testing period, process this data, and then feed it into the previously trained convolutional neural network to actually classify arrhythmia in those recordings. So to conclude, this project was able to successfully develop a machine learning model to detect arrhythmia solely from smartphone sensor measurements taken from a smartphone resting upon the sternum. It achieved a classification accuracy of above 90%, which is about on par with previous work in this field, but also just general applications of convolutional neural networks. And it's important to note that unlike previous work in this field, it was entirely autonomous. No manual data processing was required at any point through this project. A smartphone could simply be laid on the chest, and that recording would directly be processed entirely within the application and fed directly through the model to output a classification. And then finally, a cross-platform application was developed to sort of allow for an easy-to-use process for future clinical testing. So I ultimately identified 2 future goals that I have for this project. The first of which is obtaining increased or a larger amount of data. One of the main struggles of this project was obtaining data sets that were not only consistent but also viable for machine learning training. And I was only able to find 2 data sets from journals, specifically on IEEE Dataport. And Uh, that's just a main point of focus for the future. And finally, I would like to proceed with clinical testing of this application to test the viability of not only the algorithmic retrieval of sensor data, but also the final convolutional neural network processing. So with that, that concludes my presentation, and I'll now be opening the floor to questions. Thank you.